Thank you very much. I'm very pleased to be here standing in front of you. I know you also have to stand there, but at least I have a lot of space, so it's much better up here. I wanted to entertain you today about crypto bugs. So I have a presentation with a few demos. We hope that most of them will work. And the idea between the talk, the point that I want to drive is that cryptography usually is very difficult to break. Say, if you have to break AES 256, there is a small chance that somebody in the audience could stand up and say, I know how to break AES or triple DES or whatever, but the chance is close to zero. Whereas finding somebody who implements cryptography and makes a programming bug is much, much easier. We all do bugs. I did bugs. When I program, it's awful. So if you want to be sure that your cryptographic system is sure, you have to make sure it uses the right crypto, but you also have to make sure there are no bugs in it. And I want to give you a few examples where, by simple reverse analysis, we can find out what went wrong with the cryptography. There's three examples. MXI stealth, you might have heard about this one before, and eCapsule private safe and data Becker private safe also. Yeah, this is not, there's no 0 day in all of that. This is old stuff, but it's nice examples on showing how this works. So the first example is this MXI stealth crypto key. Let me find the working one. I could show it to you. I don't know if you see actually. It's a key made of two boards. There's a motherboard and a daughter board. It has a finger sensor, so you can swipe your finger on the key to make sure that to log into the system. So it's completely OS independent. You can use that on your car radio to listen to your music, or it also has a small Windows program which starts automatically when you plug it in, which can ask for your password, and then if you type the correct password, it can let you in the system and open a second partition, a second drive on the USB key where all your data is located, all your secure data. So all I've done so far is plug it in. It's as if I had found it on the floor, somebody dropped it, I took it and plugged it in here. I would need a finger or a password to log in. Let me start the debugger now because it takes a long time, and then while I talk, it can load all the libraries and stuff. So I'll just have to find this thing here. So you'll have to be a little bit patient because all of those demos, but it's more fun when we see it in reality. So here we go. So this is a key which has been certified. It's FIPS certified, so it is 142-3 level 2 certified. It means that any American agency, government agency can buy this because this is secure enough for their data. It has gone through some testing which shows that it has been well designed and well done. And the nice thing about this certification is that this is a public certification in some way. They publish the information that they give to the certifiers, to the auditors, to show why this key is so secure. So we don't even have to analyze it too much. We can just look at the data which is on the internet, and we see our daughter board with the swipe sensor and the user database storage. This is what we were going to look after. And here we have a CPU. We have an AES engine which does all the encryption. We have some memory with flash and RAM and so on. And it talks over USB to your PC when you plug it in. If you read the text which goes with that documentation, it says that the passwords of the users, so we're not looking at the fingerprint, we're just looking at the passwords now. The passwords are hashed with salt. That's a very good idea. And it's hashed with SHA-256, which is a big hash function, and then it's stored on the EEPROM on the card itself. And if you want to log into the card, you have to ask the processor to verify the password. So it's not something which is done on your PC. It's really on the card that this happens. And it does this only every 2 times a second. So you can get 120 tries per minute. There's no chance you can ever brute force this stick. And you can also program it to stop after 10 tries or so. So you can't even do it more than a few minutes. So we were asked to look at this key and say if this is safe enough for one of our customers. And so what we did is the first trick we tried, since the passwords are stored on the user database storage, which is a serial memory on the daughter board, we took 2 keys and swapped the daughter boards. And we thought my password will go on the other stick and I'll read the other data. But that was too easy. That didn't work. So we went for some more detailed attacks. What we tried to do is read out this memory. We wired some leads on it and then recorded the signals that go out when you start up the key when you plug it in. And here you can see the data that comes out of this memory. If I can... On the bottom, it's easier here, you see some user identification, then you see the name, this is the admin, and then you see some strange text. This is probably the hash, which is salted and hashed with SHA-256. We tried to make sense out of that. We tried a long time, we didn't make sense out of it. We had to give up on this part too. So then we thought, let's have a look at the software which talks with the key. Maybe there's some trick we can play. We can replay a message, say yes or no, and have it do something that it should not do. So we loaded the software in the debugger, which is what is happening right now, and then we went through all the functions, and we saw that there was a library which is supposed to talk with the card, and the library uses encryption. So all the data between your PC and your USB stick is encrypted. So with a USB sniffer, there's nothing you can do. So we tried to see if you can replay the messages or understand what they did. But again, this was well done. We just saw that after a few exchanges of messages, the key would either open up or not, depending whether the password was correct or not. Then we also saw that they didn't take much care about security in the way they wrote the code, because it was still full of symbols and debugging functions. So every time it did something, it called a debugging function, and that debugging function checked if it had to write a file or not. And it said no, so it came back, but on the stack you have the message all the time. So it says, now I'm sending something, now I'm receiving. This is was very useful and has nothing, should never be in a commercial product like this. So then we almost gave up on the system. We thought this is really well thought and well done. And the last thing we did is we tried to go through the memory of the process and see if we can find something interesting in there. So let me see if it has loaded now in here. If we look at all the memory pages and we do some... So what should we search for? Of course, now I know what it is, so it's easier. Oh, I'm sorry, I'm not going to do it this way. We could say maybe PW do hashes, password hashes, because this is what we are looking for, right? So how much easier could they make it if you can just grep for password hashes and see what's in the memory? And if you run that, you'll see that in some part of the memory you have some string constants. This is the PW hashes that it will need somewhere else in the memory. And if the demo works well, we'll find it a second time in the memory here. And here we see, oops, we have a data blob. SSD is this library which reads and writes to the USB key from the user U43 blah blah blah. This is one of those user identification we saw on the memory. And then it says the blob has the following information: password first use false, so that password has been used more than one time, and password hashes with a S. All of that. So password hashes is here, 3C. There's 60 bytes of password hashes. So 60 bytes is 3 times 20. 20 could be, 20 bytes is a SHA-1 hash of a password. This is not SHA-256 or whatever. This is SHA-1. And we see the first hash we have here starts with 0957. So let me go back to Linux and do something like, we're going to search for dragons. So if there might be a first dragon in this demo, we do some brute forcing. The first try, we say, well, maybe the password was 26C3 dragons, so we pipe that into SHA-1 sum, and then we see, here we go, 09575E blah, blah, blah. We have just brute forced the password in 2 seconds. We are just genius, right? Of course, you wouldn't start with this one, it would take much more time. But this is very, very, very different from saying every half second you can have one try at a password and after 10 times it will block. I can take this home to my PC, I can run that on multiple machines and try to crack all possible passwords. This was really weird. And then we thought, well, how can this, I'll kill this here, how can this happen? Those password hashes are actually the current password and the last two passwords. So why are there 3 passwords stored on this key? The idea is that there is an enterprise version of this key which is much better. This is for the big companies which need really, really good security. And in those companies you always have this stupid rule or this naughty rule that says every 30 days you need to change your password. And so to make sure that when you change your password, you don't use the same password again, or the password from last month, or the one from the month before, we need to store that password somewhere, or at least the password hash, a SHA-1 hash. So in the enterprise version of the software, they store the last 3 passwords somewhere on the key, but the amazing thing is they stored it on a place which is readable by anybody. You don't need to authenticate before you can access to those hashes, right? I never typed a password. I just plugged the key in, I found the password hash, I brute forced it. So if it was any of your key, I could have taken it and found your password hash. So if you want to do some conspiracy theory, you could say the NSA didn't want the key to be too secure. I have another theory. I think this was the marketing department. The engineers made this really good hardware, they scratched off all the references on the chips, this was really unbreakable, and then marketing came and says, we need something more so we can sell it to more people. We need this funny function that you cannot use the same passwords again, and they programmed it in 2 nights or whatever, and this is what came out. So what they should have done is, the best thing, of course, would have been to do the validation of the password also on the processor on the USB key. So when you try to change the password, you send the candidate new password to the USB key. It will check in its EEPROM somewhere if this is a valid password or not, and then it would answer OK or not. Or at least if it's done only by the Windows software, it should store it somewhere that you can only access once you have typed the password or put your finger on the key. That would have been the minimum that they could have done. But they were very reactive. We had a phone call with the CTO the same day, and the same week they issued a patch and the thing was fixed. So this is a story of the past. Okay, that was the first example. Now, if you think what they actually programmed, these guys from marketing or whoever it was, it's something that records every password that you type, so it knows the last passwords. So this is really a keylogger. They have invented the keylogger, but they made a bad keylogger because everybody can read out the password hashes. This is a second example. This is called the eCapsule Private Safe. I have one of these too. So what this software does, this is something that was discussed in the last talk. No, that was in another talk down there about deniable cryptography. You have some data which is encrypted and you don't want to show it to somebody. So say you have to cross a border and there's a guy at the border who asks you if you have something illegal on your USB stick, and you want to tell him, no, I don't have anything illegal, and you type a password and the stick opens up and you see vacation photographs or whatever, which is all fine, and you can get through the border, for example. So for this software has 4 different passwords. The first password will allow you to administrate the whole thing, create new passwords or change the existing passwords. The public password will give you access to one part of the documents, which could be your vacation photographs, and then the private password gives access to another part of the documents, which could be whatever you're just going to bring to the guys of WikiLeaks or whatever. I don't know what your private business is, but things you don't want to show to everybody. And then the 4th password, this is very important. There's a panic password. You type this one in, and it shows an empty folder. And you cannot make a difference between a folder that was always empty or which has just been emptied now because you typed that password. So when somebody asks you to type a password, you just say, OK. And you can choose, you want to have vacation photographs, you want to have your private stuff, or you want to have an empty screen. This is really, sounds very useful. So how does this work? It stores all your data in 2 files. I think we can look at those files somewhere on this U3 system, I think. It's in documents. There's different applications on that U3 stick. One is private safe, and it has safe.eck and safe.efs. EFS is the file system, which is encrypted with this software, and ECK is some sort of control block. I'll show you on the screen. You'll see how it looks like. It looks like this. So it's a short file with some binary data in there. And if you look at it, this data is made of 4 different blocks. And every block starts with something very distinctive. There is a ASCII 0 here, it's 30 here. And then there is an ASCII 1 here, and an ASCII 2 here, and an ASCII 3 here. I cut the last part, but it's the same size of block. The last 3 blocks have the same size. The first block is a little bit bigger. So there are 4 blocks in that control file. And if you do some reverse engineering, if you go into the code, into the debugger step by step, you'll find out how those blocks are encrypted. You find out that what they use is AES 256, which is very safe, in CTS mode, which is a mode that is not used very often, where you don't need to do padding. It's very much like CBC, but you don't need to do padding. So I guess it's for the lazy people who don't want to pad their data. So you need a 256-bit key, and that key is the SHA-256 hash of your password. So when you type a password, this will be hashed with SHA-256, and then this will be the key for encrypting your data. And the encryption algorithm also needs an initialization vector, something to initialize everything. It's like a salt in a password hash. And what they take as a random initialization vector is another hash. It's the RIPE MD160 hash of your password. So it also depends on your password. And then if you look at once you find out this, you can decrypt the block by hand, actually. And if you decrypt it, you can see what it's in there. So we're going to try to do that by hand. Fortunately, sorry, I've done that before. So I've copied the content of that on my Linux partition so they don't get into each other's way, but we have the same files that we saw before. So if we go into private safe, we can see this control block. Here it is all encrypted. And now we're going to do all this encryption I told you before. I've done that the last half hour, so I'm sure it's going to be easier now. So what we do, we set the password to be admin PW. That's the password I have as the administrator password. And then I'm going to take my encrypted control file. I'll pipe it into OpenSSL with AES 256. The key of AES 256 will be, again, the password piped into OpenSSL to do SHA-256. And the IV is, again, the password piped into OpenSSL through RIPE MD160, which is too long, so we have to cut it, and we'd only take the first 32 bytes. We're very, very happy to have OpenSSL because it would be a pain to do all of that by hand or to program it, right? So we're going to try with admin PW. And now we see it has decrypted the first block of this file. And in this block, we find the username, and we see 0 has the password admin PW, 1 has the password public PW, 2 has private, 3 has X. X is my panic password. Remember, this is the panic password. I'll use it later. It is only 1 character long, so when I type it and you see only stars, you'll know that must be the panic password because the other ones are much longer. So if I used the admin password, I'll see the first block. If I use any of the other passwords, I can try, oops, I'm sorry. There it decrypted the part about the public information. It only says the same thing, Philip hardware software. For some reason, it's always the same plain text. I have no idea what this does, but it's enough to find the bug. You don't have to understand why the bug is there. So if I have the private password, I get the next block, and if I give my panic password, it should decrypt the last part of the file. Here we see Philip hardware software. So we know now how this thing works. Now this is no big secret, right? I mean, we've reverse engineered. We know it does AES encryption. So what can we do now that we found out about this? What could be the trick? What could be applied? I'm sorry for all that switching. So this is what we just did by hand. This is the blocks if you decrypt them clearly. And this is what we could do. See, we have this file which has those different blocks. So maybe we could try to exchange the blocks. We just cut the whole key block of the public password and the one of the private password and exchange them. And we try to see what the effect is of doing that. Or does anybody have any better idea even? The panic password, of course. We can use the panic password as the private password, for example, the shredding password as the private password. And then we can do it even smarter. It's really a mess to take all this block there and exchange them and make sure you don't lose anything. So maybe you can do it much easier. Actually, we can just look at these ASCII characters. Remember the ASCII 1 and the ASCII 2? So, let's do some real hacking now. We take some very, very advanced tool. That's for the next demo. So we try to open, maybe it's still here. No, so we try to open on documents, private safe ECK. And then we use our hex editor eyes to find where we have the 3, and the 3 becomes a 2, and we try to find the 2, and the 2 becomes a 3, and we save the file. Oh, that's the demo effect. So let me, no. Let's see. Well, I'll do it again. I told you if 2 out of 3 demos work, we'll be happy, so. We don't launch anything, we just open the file. We take the 3, we make a 2, we take the 2, we make a 3, we save, yes. And then we do all the fancy launching, eCapsule private safe. It's going to have to look for everything. So let me just go on with the talk. So we find out that we can access the private data by using the panic password. Now, if you think about the utility, the reason there is a panic password, it should really not be possible to decrypt anything with a panic password, right? If it was well programmed, it would say, oh, panic password, let me just throw away the encryption key, erase all the data, wipe everything, and then create a new folder from scratch. And never ever touch the actual encryption key from any distance. So now I'm going to type the panic password. It's only 1 character. And if the demo works, we should have the private safe, the secrets. There you go. Thank you very much. So you would say this is really a strange software, right? I don't want to call any names. But so we called the company and we asked them, see, our customer doesn't want your software, it's no good. And they say, I'm sorry, I'm talking and doing. Yes, go away. So we called up the CEO of the company, and he said, well, my software works as advertised. If you look at the ad, it says you have 4 personal passwords. They are yours. Don't ever give them to anybody. If you give your panic password to the guy at the border, it's your problem, you shouldn't. I said it doesn't, it works as advertised, this is a personal password. And also, when I asked them, well, but you know, there should be other way of doing it, like if I did not put the private password into the system should not be able to decrypt the private information. Then they said, well, you know, but you are bad guys, you did some reverse engineering. There's no way, we can't protect against that. You know, as good as me, reverse engineering is just too strong. And then we had to talk about cryptography and make the difference between, you see, good cryptography is an intricate lock that you can not pick. And bad security is when you put the lock on the outside of the door, right? And everybody can remove it. So they should take a good lock and put it on the correct size of their door. Right. So the last one, this is a very old software which doesn't exist anymore, but we have this customer who says, I still have this old container with information in it from a software, and we'd be happy if we could brute force that to get access to that software. Is there anything that could be done with it? And I forgot to take my requisite for this presentation. It's the small yellow booklet from Data Becker. Maybe you remember those with the instructions. And on the second page or so, it says, Gute Software muss nicht teuer sein. So this, I got it for €5 on eBay, so it was really cheap, but I think it really was cheap also in the way it was built. So what does this software do? Oh, let me just start it and boot up the debugger again. So I have my private safe here, which I could want to open. And then, those were the days, right? You don't see many of these anymore. So let me just attach that again so that we can talk. Okay, so let it do its magic, and we go back to here. So what it does, again, there's a file system, and there's a control block, but in this case, the control block is at the beginning of the file system. So it's one huge file with the control block and the file system in it. The whole file system is encrypted with Blowfish, which is a very good encryption algorithm again, so it's a very good lock, very complicated. And they use CBC mode for the encryption, which is also a good mode. And the initialization vector they use for CBC is the same all the time. It's a constant. That's not very nice. So it's 0, 1, 2, 3, 4, 5, A, B, C, D, E, F. That's the initialization vector. They took some crypto textbooks, I guess, about encryption, and they saw this example, and I thought, that's a nice example, I can remember that. And then they used that, right? Then what we also saw is that when it starts decrypting the file system block by block, the first two integers of the block are some low numbers. It's probably the count of the block or whatever. Again, we don't understand everything, but it's enough for us to understand the bug. So there's a small number, there's 3 bytes of 0 and one value between 0 and 10 or something like this. So from this we can know whether we have a right key and we are succeeding in decrypting the block or not, right? So knowing all this information, let us see if we could do some brute force, try all the passwords and see if we get lots of 0 bits in the blocks in the beginning, but this would be very slow because Blowfish was designed to be very, very slow on the key schedule on purpose so that brute forcing would be very slow. So we loaded the debugger and tried to see how this thing works in here. So I let it run. And I type the password, which is test1234. So we'll see if we see it appear somewhere in the program. It's a little slow, but it should appear. There we go. Öffnen. And there I have a breakpoint at some funny routine. So we see this routine is being called. It has a parameter which is the password here, test1234. And for those of you who can read that, for those of you who can't read that, I'm just going to explain to you. This is a loop. It's going to loop over all the characters of the password. So this is the first part. It subtracts 1 to the length of the password, and if it's 0, it stops. And if it's not, it goes on. So 8 times it's going to go through this loop. And what it does, it shifts left there's a variable at EBP-4, which is going to be shift left at every loop. And then somewhere later, there's going to be an XOR with the current byte of the password with this shifted other byte. And then we go for the next password, we shift again, and we XOR with the next character. So I'm not going to do all of that by hand, but you get the idea. So we'll see you see now it only says est1234. It takes every character one after the other, and it creates this shifted XOR of all those characters. I think that's enough. I'll show you the rest on the slides. Let me just let it run, so maybe we can look at it later. So what is that? This is somehow a checksum. This programmer thought, well, what happens if the user types in a wrong password? And then I decrypt my whole file system with the wrong key, and then I have a file system which just means nothing, with pointers which go all the way, and so this is really bad. I have to do all this error checking afterwards. I don't want to do that. I want to be sure the password is correct before I ever try to decrypt the file system. So I'll make this small checksum and I'll hide it somewhere in the control block so I know if the password is the correct password or not. And this is exactly what happened in this routine. So we see here we have test 1, 2, 3, 4. We start at the beginning and then we shift it all the time. So the first character is the one which is most shifted actually, and all the characters are like this. And we have the XOR of all the characters in this checksum. So somewhere in the beginning of the file we have 2B72. If we open our hex editor we should see that, or small r and plus in ASCII in the file at some place at the beginning of the file. Now this is great because this is somehow a check function, but this is not a cryptographic check function, right? This is a check function that they invented on the night when drinking some coffee and trying to find out how to fix the problem. They came up with this idea. And if you look at it a little bit, you can find out that, for example, we know immediately the length of the password. It should be, since we have a 1 here, there should be at least 7 characters in the password. There could have been a 1 here if this was a 1 also, but it can't be less than 7 characters because there would not be a 1 here. So this is a first hint. That's already useful. But then what is even more useful is we know that the last character has a 0 bit at the end. So this is an even character. So if you want to brute force, we will only use even characters here. And if we choose an even character like 4, we can then see that the next one must be an odd character because we have a 1 here, we have a 0 here, so there must be a 1 here too. So from each of the characters of the password, we know 1 bit. So we just reduce the size of the characters by half. We have half the character set from all the possibilities. And what is even more useful is that once you've chosen 1 for all those characters, for the last one you don't even have to choose any random character, you can just calculate it. If you have chosen all of these, you can just calculate by XORing with the checksum what the last character should do. So what we saved here is we reduced the character set by 2 and we removed 1 character from the password. And depending on the character set, this can be much, much faster. And then additionally, this is just some shift and XOR operation. This has nothing to do with the initialization of blowfish. So we don't do any blowfish, we just do this type of operations. So let us see, so this is what I just explained to you. What the simple attack would be is to generate many, many passwords and to check every time if they have the corresponding checksum. If the checksum is wrong, we know there's no need to go through the whole blowfish stuff because the password is wrong anyway. And this is what we did first. We took some large dictionaries. We knew where the software was coming from. This was not the German version. So we took some dictionaries of that language and we found out of our thousands of words, there were 2 words which matched the checksum. And we said, well, maybe this is it. So we typed this word into the software, and then the software just crashed. It didn't show any message or anything, it just died. Because you can understand, it checked the checksum, it says, oh yes, it must be the correct password, so let's go decrypt everything. Oh, there's a pointer who says it's all the way there. Let me fetch that memory or whatever, and then it just crashes. So this is not enough, right? So once you have a candidate with the correct checksum, you still have to do the decryption with blowfish and verify that the 2 first integers are small numbers, are close to 0. So that's the other attack. If you wanted to do it more efficient, you create a program which only generates passwords which have the correct checksum. So you never ever have to try to do something if the checksum is wrong, but you brute force through all combinations which have the correct checksum. So the way you do that, if we go back to the last slide, you know that for the last character, you have to choose an even character, so you choose for the last one only the even ones, so there's only half of the character set, and then you check for the next one the even or the odd ones, depending on the next bit of the checksum and so on, and in the end you can calculate the last one. I have an example here. I don't want to go into all the details, but you get the idea. We have already chosen the 5, where is my pointer, the 5 first characters, so now we are at the last 3 characters. So for I2, for half of the character set size, depending on one of the bits of the checksum, we choose the characters from one set or from the other set. And for each of the ones we have chosen, then we can add them to the checksum and try the last but one character. It's the same thing. We look at another bit of the checksum to define if it's from the even or the odd characters. It's not very readable, I'm sorry, but I didn't have that in idea when I wrote the code. I didn't think I had to show it to so many people, but then you get the idea. In the end, the last character of the password you can just calculate from the checksum. Then this gives you just some character which is necessary for making the checksum correct. In this case, we were looking for low alphanumerical password, so we knew it has to be larger than 96. If not, then this is not within the case that we are looking for. And then if we also have this condition, then only we do this blowfish initialization. And we try to see if the result, here we have the initialization vectors, if they are really 0, 1, 2, 3, 4, 5. And this is where there is some information which we don't know, which is a small number, so we mask it out. And then we should have 8, 9, A, B, C, D. On the second integer, if there's 3 zeros also there. And if we have all those combinations, then most probably we have found the password, and we print it out, and then we can type it in, and in that case it worked. So the result is that we can now break it much faster because, as I told you, Blowfish was designed in a way that it was very slow to set up the key. When it's set up, it can encrypt very quickly, but to prevent brute forcing attacks, the key setup is very slow. So you get about 25,000 brute force trials or encryptions per second if you do it on a normal processor core. So it could be took a very long time to crack, for example, a 9-character alphanumerical password. With our method, if you have this checksum and you only try the ones which have the correct checksum, it would be 15 times faster. So if it's like 1 week and 15,000 weeks, you see the difference. In our case, we just did a test run with some very simple passwords, which were only lowercase alphanumerical, and we had the lock that this was the case. So we had a 9-character password made of lower letters and no numbers, actually. It took us 2.5 hours to break it instead of 1.7 years. Of course, the 2.5 hours came after 5 or 6 days of work, right? You try to find the thing, and then you program it, and then it takes 2.5 hours to break it. So sometimes it's worth spending the effort of understanding how it works before you just use the brute force, right? Okay, so let us see. Well, now it's open. We've seen the routine. We let it run. So it shows you all the different files that you have in there. There's no file in this one. See, it has a folder for all your different things. There must be a dragon hidden in this example also. It's here. You can store your passwords also using this Databacker private safe. And here they are. If you bearbeiten the things, it tells you, here they are, dragons. So that's your password. Okay, so this was the third demo. So what do we learn from that? We should come to a conclusion now of the talk and say, well, from looking at all of it, we can learn very interesting things. We can have fun. I think this is the first thing. There's not much more that we can make a quiz. Oh, I'm sorry, I forgot about that. There's a quiz. So you saw all these strange cryptographic functions that we saw. We've reverse engineered, we understand how they work. And all of them have the same flaw that I did not mention. I tried to not mention that flaw or not in details, that you could also use to try to accelerate breaking of the system. So do me a favor, remember what that is. Anybody? Rainbow tables, yes, thank you very much. So there we go. None of them uses salt or an initialization vector. We saw the very first one. The first one was this MXI. This did just a SHA-1 hash without any salt. You can find free rainbow tables on the internet to break that quite quickly. The second one was this one. This has a specific function. It does a ripe. The initialization vector is the ripe hash of your password, so it's not random either. But you can't find a rainbow table that does that already on the internet, but you can build one. You can spend some time creating that rainbow table and then breaking it. And you could create also a rainbow table for Blowfish, for the one we saw in the last example for Databacker, because in that case also there was an initialization vector, but it was always the same 0, 1, 2, 3, 4, 5, 6. A, B, C, D, E, F. So in all the cases, we could have used rainbow tables to break the system, but we would have to produce them first before we can use them, right? Okay, so what can we conclude from all of that? Cryptography is hard to implement correctly. You all knew that, right? This is nothing very new. But still, we find it again and again when you look at different softwares. This was all done last year. We had to look at 4 systems, and 3 of them are the one I'm presenting here. The last one was okay, so we see it's astonishing how many of those systems are actually not well made. So if you don't have the source code, the only way to know if your data is well protected is to do reverse engineering. And what you can do with reverse engineering is find the errors, right? When you find an error, you can say, there, this is not good, I can break your system because of that. When you don't find an error, you can validate that they do 20 times the hash function, and 20,000 times the hash function, and not only once, and that they sort their hashes, and then they use triple des or AES correctly. Even if you do all of that, you cannot be sure that on Monday mornings, every second month, they don't encrypt the data or whatever, right? You never have the certainty that there's not some backdoor or even more stupid error that you could not see. So if you have to choose a system which has to safeguard all your information, you should prefer open source, free software solutions, or at least open source solutions, where it is much easier to find the errors that might be in there, and much cheaper because you won't spend so much time trying to debug your system. Okay, I was a little fast, but I'm sure you also want to ask some questions or so. So your questions are welcome.
If you have questions, please go up to one of the 2 microphones in front. There's one, I'm looking at it, and one further back by the AV guy. What? Oh.
So no questions?
I'm sorry.
I can't see you. Yes.
How many of the systems you debugged actually did erase the data after they were used? So the plain text password got erased out of the RAM after the initialization of the system was done.
This one did this. So remember we saw this password hash in the memory. At some point it disappears again from the memory. And also when you do the login, at some point it disappears again. So the part which is well done on this stick also erases the memory. On the other ones I did not see that.
So most of the programs don't erase the data afterwards of the clear text password?
Yes, definitely. There's a question there.
Any more questions?
Yes, hello. Would you have found these mistakes in implementation if you had the source of these things? And is there an additional benefit to do reverse engineering after inspecting the source, for example?
I think the last 2 ones we would have found quickly looking at the source. We would have understood how it works. We would understand that this eCapsule private safe uses the same key for all the data. This would be very evident. We would have found this checksum function. Maybe in the first case, we might not have found immediately that the memory was already accessed before we had typed the password. Maybe. So maybe there might be an advantage of still doing the reverse engineering after looking at the code. Maybe when there's many different modules which interact at different times, maybe by reading the code you don't know at which time the code will be called and will be used. Yes?
Isn't the idea of the panic password for the second product bogus? Because everybody knows that it kills the data if you type in the panic passwords. So if I was an attacker, I would just copy the contents of the files first, try the password, okay, it nuked it, that was a panic password, restore the files, and go kick the man again to give me a new password.
Exactly. So yeah, absolutely. If the person at the border knows the software, he says, I know there's 4 passwords, so let's make 4 copies of your key, and then type 1 different password in every copy, and let me show all the results, definitely. So it's not really undeniable cryptography, which is actually a very difficult problem, to make a software which allows to be undeniable, because if people know this is this type of software, then they know you may have more passwords, and they will ask for all the passwords. More questions?
Go ahead. I think we have one right here.
Okay, thank you very much then.
Oh.